And dear all, in this clip, I'll try to briefly discuss on the equation for design of shaft, which we use for a circular shaft, the torsion equation. So we all have heard of the equation theta equals TL by Gj. So at first, let us assume that there is a bar of circular cross section like this. This is the axis on which we apply torque T like this. Now if we take the side view and the front view of it, it will be something similar to this. This is how it will look from the side, and this is how it will look from the front, the cross section, which is a circle. Now this is the axis. We take 2 points here, C, D. This is the center of the circle O. This is D, so this will also be D, because it is essentially the same point. From here we are looking it from the side, and from here looking it from the front. Now if we apply torque like this, for example, I have rolled up a paper. So if this is a circular shaft and I apply torque like this, twist it, so you can see the point moves along the direction of the force, right? So on application of torque, I'll draw it again. C, D, on application of torque, D goes into D dash, so there will also be a D dash here, and this is O, this is D. Now this is CD dash, so from CD it becomes CD dash, same at this side. Now we will take both of these triangles one at a time. So at first, if we take this triangle, C, D, D dash, this is phi, the shear strain, and this is, if we look at it from this direction, so it is O, D, D dash. This is theta, which is the angle of twist. Now from this triangle, we can see that tan phi equals dd dash by cd. Now dd dash, we'll write it like this only, and cd is the length of the shaft, which is L. Now for extremely small angles, tan phi would be phi. We can write tan phi as phi. We can approximate. So phi equals dd dash by L. Now from this triangle, we can see that we have learned in our childhood that S equals r theta, where S is the length of the arc, r is the radius, and theta is the angle. So using this, we'll write dd dash, which is the length of the arc, is r times theta. R is the radius of the cross section, the circular cross section. So if I put the value here, so it will be phi equals r theta by L. So we have this equation. Now also at the same time, we know that G equals tau by phi. You can write phi will be tau by G, and here we can see phi is r theta by L. So it will be r theta by L. So from here we can write the equation that tau by G equals r theta by L. Now moving on to the next part of the derivation. So what we already have, tau by G equals r theta by L. We have already derived it in the previous page. Now here, we'll take a deeper look at the cross section, at the circular cross section. So this is the circular cross section, and inside this, the whole thing which we have taken is r, the radius. Now inside this, if I take a small strip, if I take a small strip, so this is the circle, I take a small strip here like this. So from here to here, this is r, and the thickness would be dr, which is this. Now for the small strip, we'll try to find the shear stress on this strip, which is tau 1. We'll try to find tau 1. Now previously know that tau by g equals r theta by l. From here we can rewrite this: tau by r equals g theta by l. For a certain shaft, g theta by l would be constant, so tau by r would also be constant. So for this shaft, if it is tau 1 by r, it will be equal to tau by r. So from here we can find tau 1 in terms of tau by r. So this is our constant. Tau 1 in terms of tau by r into r. Now at the same time, we know that shear stress, which is tau 1, is F by A. F is the force applied. So we will rewrite it as F by, what is the area? Area is the 2 pi r into dr. Or we'll substitute the value of T1 from here, which is tau by r into r equals F by 2 pi r dr. So we will get F in terms of r. So if we write F from here, it will be tau by r into small r into 2 pi r dr. So what we are trying to find here, we'll try to find torque, the torque applied. Now the torque applied on this strip, so here we have seen that we are applying a torque T on the whole shaft, but for this strip, the torque applied would not be T, it would be dt. So torque, if torque is dt, then it would be force into radius. The radius is from center to the strip, which is a small r. Now we have all the values. We have f, so we will substitute f like this: tau by r, 2 pi r cube dr. We'll integrate dt from 0 to r. So 0 to r dt. R is capital R, which is the radius of the entire shaft. This is r. So dt would be, we'll take out the constant from inside r cube dr, 0 to r. So it will be 2 pi tau by r to the power 4 by 4, 0 to r, pi by 16 d cube tau. So this is the equation of torque. So what we have here, we have found torque in terms of the diameter of the shaft and in terms of the shear stress. So this is our, if this was our equation number 1, this would be our equation number 2. Yes. We'll take out the shear stress. If we take the shear stress from this equation, tau would be 16t by pi d cube. But also from the previous equation, we have learned that tau by r equals g theta by L. Now if we substitute tau, let us rewrite its tau equal to g theta r by L. If I do tau is 16t by pi d cube, and we'll write g theta r would be d by 2, d by 2. So it will be, the L would be there, sorry I forgot the L. It would be t divided by pi by 32 t to the power 4 equals g theta by L. Now what is this? This thing is polar MOI. T by j equal to g theta by L. So we can finally write theta equals TL by gj. This is the equation of the angle of twist which we use for design of shafts, design of circular shafts for various applications. So I hope you have find this video helpful, and for any further doubt, please leave your comment down there so I can address it in my future videos. Thank you.